Hello students, welcome to my channel Engineering Education. Please subscribe my channel. Thank you. In this lecture we are going to solve problem 1.10, chapter 1, Introduction and the First Law of Thermodynamics, from the book Applied Thermodynamics by Eastop and McConkey. Statement of the problem is: the gases in the cylinder of an internal combustion engine have a specific internal energy 800 kJ per kilogram and a specific volume of 0.06 cubic meter per kilogram at the beginning of expansion. The expansion of the gases may be assumed to take place according to a reversible law, PV power 1.5 is equal to constant, from 55 bar to 1.4 bar. The specific internal energy after expansion is 230 kJ per kilogram. Calculate the heat rejected to the cylinder cooling water per kilogram of gases during the expansion stroke. So if we discuss the statement on the PV diagram, so this is the rough sketch for this problem. This is state 1. Before expansion starts from here. This is pressure P1, 55 bar. Here we have specific volume V1, which is 0.06 cubic meter per kilogram, and then law of expansion is PV power 1.5 is equal to C. At state 2, after completion of expansion, we have P2, which is 1.4 bar, and V2 is unknown at this point. The specific internal energy at point 1 is 800 kJ per kilogram, and at state 2, after expansion process, it has specific internal energy which is 230 kJ per kilogram. So we will write the given data from the statement. So P1 is 55 bar, and P2 is 1.4 bar. Specific internal energy is 800, U1 is 800 kilojoule per kilogram. Specific volume V1 is 0.06 cubic meter per kilogram. Expansion law is PV for 1.5 is equal to C, which is constant. U2 after expansion is 230 kilojoule per kilogram. We have to find only one thing in this problem, and that is the heat rejected, which is Q or QR. We can represent it with QR, heat rejected, as simply Q. So coming to the solution of this problem, we will first find the value of V2, which is unknown to us. So for that we have P1 V1 power 1.5 is equal to P2 V2 power 1.5. So in this case, P1 V1 and P2 are known to us, only V2 is unknown. So in this case, V2 power 1.5 will be equal to P1 V1 power 1.5 over P2. So putting the values in this, we can write that P1 is 55 bar, so converting it into Pascal, factor of 10 to the power 5 will be multiplied with this, and V1 is 0.06 cubic meter per kilogram divided by P2, which is 1.4 bar, converting it into Pascal. So simplifying this and solving for V2, we get the value of V2, which is 0.695 cubic meter per kilogram. So this is the value of V2 at state 2. Now from this we can now apply the expression of work done. So work done from 1 to 2 is equal to minus m integral from 1 to 2 P dV. Further, we can write that, as we know that C is equal to P V power 1.5, so equating for P will be equal to C by V power 1.5. So putting P over here, W will be equal to minus m. The value of m is taken as 1 kg. It is assumed as 1 kilogram of mass. So putting it over here, we get integral from 1 to 2 C by V power 1.5 into dV. Now further applying the limits of integration, so W is equal to, when we apply the limits of integration, we get C is constant, and we can write it like this: C into 0.5, minus sign will be there, so we get this minus sign will cancel. The effect of minus sign will become positive, because it is, when we apply integration, minus 1.5, so there will be plus 1 with it, so minus 1.5 plus 1 is equal to minus 0.5, so it will become positive. So C by 0.5 1 over V2 power 1.5 minus 1 over V1 power 1.5. So putting the values, we know about these values, and also the value of C can be calculated from P1 V1 power 1.5. So C is equal to, P1 is 55 bar, so 10 to the power 5, converting bar into Pascal. V1 is 0.06 cubic meter per kilogram. So when we simplify this, we get 80833 Newton meter cubic meter per kilogram, power 1.5. So putting all the values here, we get W is equal to, the value of C is 8833 divided by 0.5 into the value of V2 is calculated 0.695 power 1.5 minus 1 over V1 is 0.06 cubic meter per kilogram power 1.5. So simplifying this, we get the value of W, which comes out minus 466 kilojoule per kilogram. So this is the value of W. Now further we can find the value of Q as required in this problem using non-flow equation. So from non-flow equation we know that Q plus W is equal to U2 minus U1. So we are interested to find the value of Q. So Q is equal to U2 minus U1 minus W. So putting the values, Q is equal to U2 is known to us and it is 230 kilojoule per kilogram minus U1 is given 800 kilojoule per kilogram minus W is minus 466 kilojoule per kilogram. So the value of Q is equal to minus 104 kilojoule per kilogram. So as this heat is rejected from the system and it is output from the system, that's why the value of it is negative. So we can also write that heat rejection value is QR is 104 kilojoule per kilogram. When we mention that heat rejection or heat rejected, so in that case it will be written as positive, and if we don't disclose that it is heat rejected and we only use the simple Q, for that there will be minus sign with the value. So this is the required heat rejected in this problem. So this is the solution of problem 1.10. Thanks for watching. Please like and comment on my videos. Also subscribe my channel to get new videos.